Welcome back to this course on polymer chemistry, and in this lecture number 22 we are going to continue the first half of our discussion on chain copolymerization. We will cover the remaining part of the chain copolymerization discussion we are having, and then take from there we start a new topic or new synthetic procedure, namely ring opening polymerization. Now, if you look at the slides, we had during last two lecture, in our discussion on chain copolymerization, we basically covered these topics, different types of copolymers, importance of copolymerization and copolymer composition, the microstructures, alternate random blocky structure, how the reactivity difference between the monomers actually give this type of copolymer microstructure, and we have talked about copolymerization composition drift with time, and then we talked about how the monomer reactivities and different types of chain initiation, types of chain initiation actually determine these values of the reactivity ratios. In today's lecture, we will just cover this three topic. We will talk about QE scheme, and then very briefly about ionic copolymerization, how that is different from radical copolymerization, and just a brief idea about the type of application this copolymers goes. Now, in the last lecture we talked about different factors contributing to the reactivities of the monomers, and in turn the reactivity ratios, the value of the reactivity ratios of these monomers. We talked about the resonance stabilization of the substituted group. We talked about the electron charge density, electronic charge density. We talked about the steric effect and so on. And now, all these factors actually contribute to the reactivity of the monomer in such a way that it is very difficult to distinguish the contribution from each of these factors in the reactivity of the monomers. Hence, it is very difficult to get a quantitative idea, or it is very difficult to predict the reactivity ratios of the monomers from a given structure. Nonetheless, one semi empirical method proposed by Price and Alfray is often used very commonly to sort of get the reactivity ratios of different monomers and a ranking between different monomers in terms of their reactivities. There is a semi empirical approach, and this is the QE scheme we are talking about, and this is we are continuing our discussion on radical copolymerization. So, it is applicable for radical copolymerization, and this scheme is based on the assumption that the rate constant of reaction between a propagating radical P, this is a propagating radical P with a monomer M. Now, this rate constant can write Kpm. This is a rate constant for reaction between a propagating polymeric radical P and a monomer M is given by this expression, where these two terms are the reactivity measure of the reactivity of the polymeric radical, and this is the measure of reactivity of the monomer, and these two terms EP and EM, they are the measure of electronic charges, electrostatic charges on the polymer radical and the monomer respectively. So, if I write from this the expression for R 1, which will be given by K 11 by K 12, I should write. Now, this both cases the polymer radical is at the end is a same. So, this will get cancelled. So, I can write Q for M 1, Q for M 2, exponential for 1 E M 2. You can get the expression from K 11 for K 11 and K 2, and if you do the ratio you get these two, this because these are same radical 1 and 1. So, these cancel out. So, you get this, where this is the measure of reactivity of monomer 1 and this is the measure of reactivity of monomer 2. This is the charges, electrostatic charges on the polymer radical and the monomer. Now, another assumption is made in this approach is that E P 1 is same as E M 1, and we will write this as E 1. The assumption is that the electrostatic charge on the polymer radical, which has at the end a monomer 1 structure, and the electrostatic charge on monomer is same, and which we writing as E 1. So, similarly, we can write E P 2 E M 2 as E 2. So, again the assumption is that the electrostatic charge on the polymer radical and the monomer are same if the monomeric residue at the end of the polymer radical is same as the monomer we are talking about. So, if I can write similarly for R 2 Q, now because Q is always talking about always related to monomer. Essentially, these two relates the reactivity ratios of the monomers to the electrostatic charge on the monomer. We do not have any term which is related to the polymer radicals. These all the terms are related to the monomer. So, basically this relates to the reactivities of the two monomers and the electrostatic charge on the two monomers. Now, if we multiply these two, we get this value for R 1 R 2, which is basically the measure of, we have seen earlier, is measure of alternating tendency. If it is close to 0, then the monomers will produce a alternating microstructure. If they are close to 1, then the two monomers will produce a random copolymer, and if they are equals both are equals to 1, then obviously R 1 R 2 will be equal to 1, then that will be exactly random copolymers. So, R 1 R 2 will be given by, if we can multiply these two, it will be given by exponential minus E 1 minus E 2 square. Now, this expression is in sync with our understanding till now. Now, if E 1 is very close to E 2, that means the electronic charges of the double bond in the monomers are very close, then obviously this will become close to 1 and we get a random copolymer. Now, if the double bond for the two monomers has different electrostatic charge, if they are, then they are, what will happen, R 1 R 2 will be close to 0, that means their reactivity, they will produce a more a copolymer which is more closer in alternate copolymer rather than a random copolymer. So, if E1 minus E2 goes up, then it will be an extreme for say E1 is E2, we will get R1 R2 close to 1, which will give ideal copolymerization as we expect. And if they are if this is goes down, so they are equal, and then you get this. If they are different, then R1 R2 will be closer to 0, producing a alternate copolymer, which is in sync with our understanding whatever we have discussed till now. Now, how do you get these values for Q and E? Now, arbitrarily it has been assigned styrene has been assigned sort of arbitrarily a value of Q is 1 and E is 0.8, and rest of the monomers are compared with the value of styrene. What happens? Individual monomers are copolymerized with styrene, and from the experimental values of R1 and R2, you can use these expressions, where if you consider 1 as styrene, then you know Q1, you know U1, hence you will from these two expression, and you also know R1 from experiment, R1 R2 from experiment. So, from using these two expression, you will be able to find out the values for Q2 and E2. So, monomers are copolymerized with styrene, and you get the experimental values of R1 and R2, and from known values of styrene having Q is 1 and E is minus 0.8, you can get the unknown values for the second monomer. And once you get the individual values for different monomers, they are those values of Q and E are further defined by copolymerizing monomers other than styrene. So, basically you first copolymerize with styrene and get the experimental values of R1 and R2, and get from the expression you get Q and E for the unknown monomers, and then it refine further these values of Q and E for the other monomers by making copolymers between them. Now, obviously, this is Q is a measure of reactivity as we have seen, and E is a measure of electrostatic charge. So, if Q goes up, the reactivity will go up, and E goes down, the value of U goes down, because it is a measure of electron density, electrostatic charge. So, basically electron density on the double bond. If there is electron donating group, then the electronic density or electrostatic charge will go up, then key value will be going up, and if there is electron withdrawing group, which basically reduces the electron density on the double bond, and hence the electrostatic charge, it will be more of a lower number. So, electron density T goes down and electron density goes up, and the value is negative, E is negative when the double bond in say this monomer, the double bond is electronic rich compared to a ethylene molecule. It is a simple plain double bond. So, if you look at few datas of the numbers for Q and E, styrene is arbitrarily taken as 1 and -8 -0.8, and if you compare with other monomers, say like other conjugated diene like isoprene and butadiene, because they can easily stabilize the radical by resonance, their reactivity is high. So, Q is high, and they also basically act as the electron donating group. So, increase the electron density in the double bond. So, basically this value is negative, and negative means is equal to electron rich, negative is a charge for electron. So, negative means electron rich. Now, if you compare the monomers having electron withdrawing groups like MMA and acrylonitrile, the reactivity comes down compared to styrene, because they cannot stabilize as much as styrene can do a propagating radical, whereas because they have electron withdrawing group, the charge on the double bond actually lower, it is more of a positive charge. So, you get a positive value, and acrylonitrile is more strong electron withdrawing group. So, it has a higher positive value compared to MMA. And compare this vinyl chloride and vinyl acetate, which is basically, as we have known from our earlier discussions done in several times, their reactivity is very low because they cannot stabilize the radical propagating radical. So, their reactivities are low. So, Q values are low, and they basically very weakly donating or electro withdrawing groups. So, the values are very low, either positive or negative, depending upon what is the net electron withdrawing effect or electron donating effect. Look at this monomer maleic anhydride. We know the structure of maleic anhydride. Now, this is a very two very strong electron withdrawing group. So, basically the electrostatic charge will be much more positive compared to a ethylene group, and that is why the value for E is quite high, positive 2.25, and these values will vary. It is not that these values are very fixed values, but this value might vary little bit depending upon the condition of the reaction, and so, but the trend will remain same. So, absolute values of this monomer Q and E value might change, but the trend will always remain same depending irrespective of the condition. And because it cannot stabilize the radical much, so their reactivities also comes down. So, in general we can write that if your monomer can stabilize the resonance the propagating radical by resonance, the reactivity is high, then Q would be greater than 5. If they cannot stabilize by resonance, then Q would be lower. So, basically Q is a measure of resonance stabilization. So, now we can so if you know these values, then we know that if the two monomers which are having very electrostatic charge, having very positive charges like acrylonitrile and maleic anhydride, they will be difficult to copolymerize. On the other hand, if you take maleic anhydride, the monomers are very much electrostatically positive. So, homopolymerization of maleic anhydride is very difficult, it does not happen. Now, if you take maleic anhydride and copolymerize with something which has a negative value of E, that means they have a electropositive electron rich double bond, then obviously there will be attraction between the two polarities, and there will be possibilities for the copolymerization will be much easier. So, whereas malic halide does not homopolymerize, but it can easily copolymerize with butadiene or styrene, okay, because their charges are opposite. So, the monomers can attract each other and do the reaction. So, basically now we know that with this how to what are Q and E, and how what is the basis of these values Q and E, how to experimentally or semi empirically get these values of Q and E in comparison to arbitrarily assigned values of styrene, and from these values of Q and E we now can predict whether two monomers will copolymerize or not, and their sort of ranking in their reactivities and so. So, with this we will move to we will basically completed our discussion on radical copolymerization. We will move and discuss very briefly about ionic copolymerization, and ionic copolymerization are not very often done, typically, as we have said earlier in our discussion in earlier lectures, that carrying out ionic polymerization is always difficult. So, unless there is a specific requirement, like you are making a specialty polymers, like then there is no point of making these polymers by these ionic methods. That is why these copolymers are not usually synthesized by doing ionic polymerization from a mixture of two or more monomers, but copolymerization is done by ionic polymerization to make block copolymers, where you first make a block of one monomer and then add the second block to get a block copolymers. Nonetheless, if we compare ionic copolymerization and have with the radical copolymerization, we can understand the differences, and in that way we can understand several characteristics of ionic copolymerization. Now, unlike radical copolymerization, this ionic copolymerization is much more selective. Not many monomer pair undergo copolymerization. The number of comonomer pair you can choose, which you can use to make a copolymer by ionic method, is limited, and we know that in case of radical copolymerization, basically there are numerous options where you can choose two monomers and make copolymer from there. And we know that cationic copolymer the monomers which are having electron donating group as a substituent will copolymerize by cationic method, and the monomers having electron withdrawing group as a substituent will undergo copolymerization with anionic method. Typically or generally, the tendency of this copolymerization are towards ideal behavior, because when, as I said, that the number of monomers are limited. So, only those monomers which are having reactivity towards a cation, they undergo cationic copolymerization, and the monomers which have reactivity towards anion, they undergo anionic copolymerization. So, the monomers which undergo ionic copolymerization, their reactivities are not too different. So, they typically or generally have a ideal type copolymer. They make typically ideal copolymers. And of course, like the homopolymerization, we have discussed the reactivity of a ionic polymerization will depend upon the initiator you are choosing, and the medium polarity, solvent polarity and the temperature. So if we are talking about copolymerization, the values of R will change with the different types of initiator, medium polarity and temperature. Some examples of the commercial copolymers. As we said earlier, the styrene is styrene homopolymer or polystyrene. Polystyrene is a very brittle polymer which breaks easily, and also it is very having very poor solvent resistance or chemical resistance. So, to improve what is done, styrene is copolymerized with acrylonitrile, where the amount of acrylonitrile is limited to 10 to 40%, by which you can, or the solvent resistance property of styrene is improved. So, this copolymer has much improved solvent resistance property compared to polystyrene, but acrylonitrile also are brittle. So, polyacrylonitrile is also brittle. So, this copolymer does not have a significant improvement over over the polystyrene molecule homopolymer in terms of brittleness. So, what is done? Styrene butadiene rubber is used, where a rubber butadiene having low Tg, it gives a rubbery domains in the copolymers, and as a result this copolymer becomes rubbery or elastomeric, and these copolymers are typically synthesized by emulsion or ionic polymerization. This copolymers with high styrene containing high amount of styrene are used as a latex paint, where the styrene is cross-linked little bit with unsaturated dicarboxylic acid, and to combine or to improve both the solvent resistance and impact properties of styrene, one very common approach is taken is making a sort of trar polymer, where you have acrylonitrile which improves the solvent resistance, butadiene we improve the impact properties, and styrene which gives you the heat resistance properties. So, this is a very commonly used polymer as a homopolymer as such, or as a blend with some other homopolymers like polystyrene and polycarbonate and others. Styrene can be cross-linked with a small amount of divinyl benzene cross-linker that will make cross-linked spheres, cross-linked product which can be used as a packing material for the columns in size exclusion chromatography. And there are other examples of copolymers which are available commercially, like ethylene vinyl acetate copolymers, unsaturated polyester and so on. There are other examples, but I am not spending much time on discussing those applications here. What we will do now, we will move to the next polymerization method, which is ring opening polymerization, or in short ROP. ROP by name, as the name suggests, is a ring opening polymerization. So, you have a ring, the monomer in having ring structure, and you polymerize it and make a linear polymer. Now, the feasibility of this polymerization from a ring to linear product, ring monomer to, or cyclic monomer to a linear product, like all other reactions, depends both on thermodynamic and plus kinetic factor. We have discussed this thermodynamic factor earlier also while discussing in ring formation, cyclic formation in step growth polymerization, if you can recollect from about 4 or 5th or 6th lecture, where we talked about the tendency of cyclic ring formation in step growth polymerization. The same logic applies here about the thermodynamic factor. Now, if you look the data, if we compare, so let us talk about the data and then we can understand the thermodynamic factor in more clearly. Now, these are the data of all the three: del G gives free energy change, enthalpy change and entropy change. Now, I have made it T del S to compare and put it in the same scale. This is from cycloalkane, liquid cycloalkane to linear crystalline polymers. Now, when you are talking about cyclohexane, these are basically we are talking about polyethylene. These are all polyethylene, whether you start from a 3 member ring or 4 member or 5 member, this all gives you polyethylene. Now, these values here shown here, these are all semi empirical values, they are not experimentally determined, they are semi empirical values. Now, if you look at the data, as the ring size increases from 3 to 4, 5, 6, 7, 8. Now, the ring, the lower member ring, 3 and 4 member ring, they are quite highly strained. 3, 4 members are strained because of bond angle strain, they are having high energy because of bond angle strain. Whereas 5 member ring are strained due to eclipse conformation, and 7, 8 member ring having also strain because of transannular conformations. Now, if you look at these numbers, the enthalpy change on polymerization from a 3 member cyclic ring to a linear polymers, it is highly negative, and if you just talk about linear polymers, what about, first let us talk about del S. Now, del S will be negative because the monomers are getting joined and making a linear polymer. Now, if you talk about the same molecular weight, obviously if you have a larger ring, less number of monomers you require to make the same length of polymers. So, your del S would be less negative if your ring size is larger. So, if you can, and if you see that if your ring size increases, your del S value is decreasing, is becoming less and less negative. But if you follow the del G value, gives free energy value and del H value, they are almost having same trend. So, basically the polymerization, this polymerization is dictated mainly by the enthalpy change. Because 3 and 4 membered ring are highly strained, when they open up and polymerize, they gives up lot of this energy which was already which is getting released because of ring opening. Similar also true for high rings with size of 7, 8 carbon. 6 membered ring is actually little higher than 0, if you compare it is slightly higher than 0. Basically 6 membered ring is not thermodynamically feasible. The ring opening polymerization of 6 membered ring is not thermodynamically feasible. So, basically now from this thermodynamic data we know that it is easy to ring opening to carry out ring opening polymerization on 3-4 member ring and say 7 member ring. 5 member ring also will polymerized by ring opening method, whereas 6 member ring is not that feasible to or basically is not feasible to polymerize thermodynamically. However, can you take a say 3 membered ring or a 4 membered ring and or say 5 membered ring? Can you make polyethylene by this route, this way? Can you make polyethylene from either of these by ring opening polymerization? The answer is no, because it is not only determined by thermodynamic feasibility, there has to be some kinetic pathway through which you can carry out the polymerization. Basically, this is saturated ring and there is no place where you can carry out a say electrophilic or nucleophilic attack by external and open the ring and then carry out the polymerization. So, these molecules, even if they are thermodynamically feasible, they do not undergo ring opening polymerization. So, what you need? You need a heteroatom in the ring, in the cyclic ring, which if you have a ring like say ether molecule, Z is ether or say a ester or say a amide, then what you can do, there is a, if you use acid or base, they can actually do nucleophilic or electrophilic attack on this ring and ring open, and then which can react with another ring cyclic molecules and let the chain propagate. So, what we basically need, what we basically now know that simple cyclic rings like cyclopentane or cyclobutane, they do not undergo ring opening polymerization. You require a heteroatom which will actually enable a electrophilic or a nucleophilic attack by external agents, by which the ring will open and then start the propagation reaction, and which will finally lead to a polymer molecule. So, the types of monomers, there is a different structure where basically these are the types of monomer you can do a ring opening polymerization. So, basically all have a heteroatom in the ring, whether it is a ether group or ester or a amide, whatever is the case. Now, that actually enables a electrophilic or nucleophilic attack from external agents, which will ring open first and then propagate. This will form and give polyphosphogen. If you have a cyclic siloxane molecule, it can open up to give you linear polysiloxane. If you have a lactone, give you polyester. If you have a lactam, it will cyclolactam, it will give you a linear polyamide molecules. Now, the chart of the thermodynamic feasibility which we shown, that was for ring cycloalkanes, not this type of monomers where you have a heteroatom. So, the absolute value in this graph will change if we consider now a cyclic ring having heteroatom, but the trains more or less remain same. So, again the trend of thermodynamic feasibility will decrease as you increase from 3 to 6, and then again go up if you increase the ring size. So, basically if you have cyclic ethers, say tetrahydropyran or a 1,4-dioxane, they do not undergo polymerization, whereas these actually undergo ring opening polymerization. Now, let us talk about few characteristics of ring opening polymerization, and we will talk about the mechanism and kinetics of ring opening polymerization. Now, as we discussed, if you have a cyclic ring here, then you need first to ring open the ring to open up and then start the propagation reaction. Now, if you have a radical initiator, say if you have a radical initiator, now it is unlikely that this will interact or react with this and ring open, that is not very feasible. So, you either need a cation or a anion to sort of initiate a ring opening polymerization. So, initiation by, in case of ring opening polymerization, the initiation is done by the same types of ionic initiators as in the case of ionic polymerization of carbon carbon double bonds. We have discussed in length about the cationic polymerization and anionic polymerization of carbon carbon double bond, and those are the same types of initiators will be used to basically polymerize the cyclic rings and make a ring opening polymerization. So, radical initiator is not basically applicable in terms of in case of ring opening polymerization. Now, because we are talking about initiation by ionic initiator, so you have those different types of species, covalent species between the ion and the counter ion, whether it present as a covalent species or ion pair or free ion, those different types of association between the reactant center and the counter ion possible. Hence, there is a T-Vendor's effect of the solvent and the counter ion in case of ring opening polymerization, as well as was in the case of the linear ionic polymerization of the double bond. Now, this is a chain polymerization. That is interesting because the polymers you are making, see if you have a lactone, you are opening up and making a polyester, or you have a lactam, you are opening up and making a polyamide. Now, polyester polyamides are typically synthesized, what we have discussed earlier, they are synthesized by step polymerization, but in this case we are making the same types of polymers which we knew till now that they are typically synthesized by step growth polymerization. They can be synthesized by ring opening polymerization of the cyclic monomers as well, and the mechanism here is chain polymerization. So, basically a propagating chain propagates and the monomers get added and the chain ends. So, the chain keep on propagating. So, there is no reaction between two monomers, or there is no reaction between two high molecular polymeric chain as well, the same as mechanism same as the chain polymerization. And because we are talking about ionic polymerization, in most cases they are leaving, and we know that bimolecular termination is not possible for ionic polymerization. So, there is, if there if you take care of your reaction medium very well, so that there is no impurities, then these polymers are leaving. So, you can make block copolymers or functional polymers at the end of the reaction. And in this case, unlike the linear polymerization of the vinyl molecules, polymerization depolymerization equilibrium is very important. Now, one different this ring opening polymerization with the normal chain polymerization we know is that the rate constant for propagation is several order of magnitude lower than normal chain polymerization. It is actually of same order like in case of step growth polymerization. So, though this is a chain polymerization, but the reaction rate or the propagation rate constant is having much lower value compared to several order of magnitude lower in comparison to normal chain polymerization, and the values are similar to the step growth polymerization values. So, the reaction is slower compared to your normal chain polymerization, and as you know that we discussed this most cases these are leaving. So, the molecular weight of ring opening polymerization is dependent on the conversion. So, higher the conversion, the higher the molecular weight, and also you can control the or estimate or predict the molecular weight from the ratio of monomer and the initiator, as in the case of other leaving polymerization we know. So, unlike step growth polymerization, here you have you can control the molecular weight by the ratio of monomer and initiator, and like the step growth polymerization, the molecular weight will depend upon the conversion, but in case of step growth the high molecular only get a higher conversion, but in case of ring opening you get slow increase in the molecular weight with the or the linear increase of the molecular weight with the conversion of monomer. Now, examples of what will before we come to examples, let us talk about the mechanism part, what are the ways this ring opening polymerization done. If we know this is ionic polymerization, so let us first talk about an ionic ROP. Now, the initiator, it is initiated by, as I said, a similar ionic initiators as in the case of linear chain anionic polymerization, like metal hydroxides or alkoxide, metal hydroxides or metal alkoxides or metal oxides, etc., or like we discussed earlier, alkyl metal like alkyl lithium or aryl metal you can use to initiate the anionic chain polymerization, or radical anion also anionic species like sodium naphthalene, they also there are same types of initiator as we talked about our discussion on anionic chain polymerization. So, what happened, say you talk about say alkyl metal initiator, you have a alkyl metal initiator, it say I take a ethylene oxide, now there is a nucleophilic attack by this initiator and the ring will open up. So, you have this, now this will again react with another monomer, again similar way. So, you can write as a general, you can increase the number of state and you will get your polymerization. Now, as I said that like other anionic polymerization, this is a living polymerization. So, this at the end of the reaction it remains like this. So, you can add a second monomer and make a block copolymer. If you want to terminate reaction, you can exchange these with say adding some water or alcohol, and then you can exchange like other we discussed earlier. Now, if we talk about cationic ring opening polymerization, now here typically strong protonic acids like say trifluoro acetic acid or fluorosulfonic acid or say triflic acid, which are very these are acids which are very strong acid, are required to initiate a ring opening polymerization. Now, let us have, so this will say talk about now a 4-membered ether. Now, in this case there is a nucleophilic attack of the oxygen to the proton, and you get you actually form secondary oxonium ion. In all these cases you have a counter ion associated with that. This will react with another monomer and propagate in the chain. So, you can make a polymer like this will form secondary oxonium ion. This is tertiary oxonium ion. Now, we have been talking that you need a very strong acid, because if your counter ion have sufficient, if your acid is not that strong, then this counter ion will have sufficient nucleophilicity to either attack the oxonium ion or a proton and stop the reaction there itself. So, for that you require a very strong acid, so that the nucleophilicity of the counter ion will not be enough to compete with the addition of monomer or the reaction of monomer with the oxonium ion. Similarly, if you have little bit of moisture present in the medium, or if you have a water molecule, then this will easily compete with your monomer with the oxonium ion and then terminate the or disrupt the reaction immediately. So, like earlier when you talked about cationic polymerization, here also you need to have a very stringent requirement of so that you do not have a moisture any moisture present in the system. Now, other types of initiators we talked about those catalyst and co-catalyst like BF3 and H2O catalyst and other types. This can be also used in this ring opening cationic ring opening polymerization also. Now, at the end as this will remain leaving, the only thing in case of cationic polymerization, as you can imagine that if your chain is having is a linear chain, at the end you have a cationic group and anionic counterant, then you can, if you have oxygen here, then it can do intramolecular reaction and form a linear molecule plus a ring molecule, and where it can also react with another linear molecules and then stop this chain and form a site in middle of another chain. So, from there a branching can happen. So, these are the side reaction where chain transfer takes place intramolecularly within the chain, forming a ring structure and another linear molecule, or if there are intramolecular chain transfer reaction happen, then there will be possibility of bunching in this case. And in this case also, if you want to stop the reaction, you can add agents by which it can external agents which will terminate the cationic chain end. Now, with this I think we have discussed the ring opening polymerization. Now, let us talk about few examples of commercial ring opening polymerization. These are the typically these are the polymers which are available commercially, which are made by ring opening polymerization. For example, polyethylene oxide and polypropylene oxide, they are synthesized by anionic ring opening or corresponding cyclic monomer of ethylene oxide and propylene oxides. Polytetrahydrofuran can be synthesized or synthesized by cationic ring opening polymerization of tetrahydrofuran. Polyacetals are synthesized by cationic ring opening polymerization of thioxane, and as I gave examples of aliphatic polyesters from lactones and polyamides from lactams, and this is also very common where linear polysiloxanes or silicones are synthesized by anionic or cationic ring opening polymers of cyclic siloxanes. So, with this we end our discussion of ring opening polymerization, and in the next lecture we will start our discussion on stereochemistry of polymerization, and subsequently in another lecture we will talk about coordination polymerization. So, we will start stereochemistry of polymers and polymerization processes in our next lecture.